All right, here's example 1, part 2 for class 16, where we're going to do rigid body acceleration. In the first part, we did the problem using vector math. And here we're going to use the acceleration diagrams, which I believe are a better way to approach the problems. And I would suggest that that's the way we do all of them. So I make 3 careful diagrams here. Best to use a straight edge if we can. I mean, my straight edge is a old driver's license that happens to be sitting around here. Okay. So I'll put my little equal signs and my plus sign right in here. And then I will apply the knowns. Okay. So the acceleration at B is given. So we'll draw that up here, right here. So that's going to be AB. And we're going to use that as the known. So we're going to place it. Well, first off, we should talk about strategy. When doing these problems, we don't necessarily know how to solve directly for C. And we would have to eventually come to the conclusion that we needed to first look at point A in order to solve for that angular acceleration. Something that we knew from the velocity analysis that we did as part of the previous example. If this was a fresh problem, we would have to do the velocity analysis first. And we would have found that omega was equal to 0.4138 radians per second, and that was a clockwise. So we're going to need that information. But in terms of strategy for solving this, we will first look at the equation acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B and tangential plus A with respect to B normal. And I might have made that equation too close to my diagram. Yeah, I think it's going to be fine. I need to draw my diagram twice anyway. It's not good to try to reuse these diagrams. Use up plenty of space. And also, an element that's good to always include in the 3 diagram method is the coordinate axis. Okay, so back to filling in our diagram here. We're going to place the acceleration of B at A, right? And one thing I know about A is that the acceleration is going to be along that line. There's some chance that it's going to be to the left. In fact, it's almost certain. I think it's going to be to the left, but we need to establish that. So let's keep it unknown for right now. And we put it at both places here. So because we used B as the reference, we go ahead and pin it at B. All right, and hopefully I didn't make this this diagram too small, because we want to be careful with the angles right here. All right, so first off, here at this spot B, there's going to be 2 different components. One of them is going to be tangential, and it's going to be along this line. The other is going to be normal, and it's going to be along this line right here. The normal one we could find right away because we know that this acceleration of A with respect to B normal is just equal to omega squared, and in this case it's LAB. It's important to look carefully at the angles that this is taking place. And that angle right here is 25 degrees, right? Because it's the same as this angle up here, right? Now what we don't know is what direction the tangential is going to go. Is it going to go up and to the right, or is it going to go down and to the left? So my approach often is to just assume a direction here and see if that works out. So I'm going to assume an angular acceleration is going to be clockwise. I don't know that. That's an assumption. Have to be careful. If I ended up getting a negative answer for this angular acceleration, I know that I will have chosen badly. But based on that angular acceleration, we're going to have a tangential acceleration come on right here. And that's going to be A with respect to B. This is the difficult part in doing these. And often, actually, one of the other elements that's difficult is looking for these angles. And that guy right here, he is also 25 degrees. So what we find when we go to solve this and try to get, our goal at this point is to find that angular acceleration. So we do it in the y direction. Why do we? Because we know that the acceleration of A over here on the left-hand side right here is going to be 0 in the y direction. So I go y dir, and this is 0. It's going to be equal to the acceleration of B, which is upwards, and that's 0.5, so it's positive because it's upwards. And now we have to go over to the diagram to the right-hand side. And in the y direction, we're going to have, by the way, this is going to be alpha times LAB. Alpha times LAB, which is 4 feet, but only the cosine of 25 degrees of it. And then we're also going to have a negative, because you can see that this, for the normal part of the thing, the normal component is pointing downwards in the y direction. So this could be a negative omega squared, or 0.4138 squared, times our LAB, which is 4, and now it's going to be, but that's going to be the sine of 25 degrees. In doing that, we solve for alpha, and what do we discover? We discover we get a negative answer. Oh no. So we got a negative 0.0580, whoops, let me fix that, 808 radians per second squared. So we chose poorly. This guy right here was wrong. If we wanted to follow through with this analysis right here for the point A, we would then follow with the x direction. And an interesting thing interestingly enough, it let's see, I believe, I'm looking at these numbers, I'm trying to see if we had made that conclusion already. Yeah, okay, yeah, we got that. And so we did get, yep. So we got that same answer. We did get that this was alpha was actually 0.05808 radians per second squared counterclockwise, right? That was our conclusion. And if we follow through in the x direction, what we end up finding is we have, actually there's a acceleration to the right, which seems a little weird to me. I don't quite like that. I want to double check that, that I didn't make some mistake along the way. This is something that happens quite often when you're doing a analysis. But I'm saying my result is going to be in terms, let's see, it's going to be acceleration of A is going to be equal to, okay, so this, right here I'm drawing it as positive, the acceleration of A, right there, acceleration of A, and it's going to be equal to 0 here in the second diagram, and then it's going to be minus, right, because maybe I should redraw on this and make it messy. This is the actual direction that A with respect to B, the acceleration of A with respect to B in the tangential direction, because it's actually coming this way right here. This is the actual one. So continuing on there, that's in a negative x direction, and that's going to be our 0.05808 times 4 times, and now it's going to be the sine of 25, right? And then, but we're also going to add in plus the 0.4138 squared times 4, and now the cosine of 25 degrees, okay, because that's still to the right. That's this guy right here, right? And we know it's the cosine because it's like, you know, it's this adjacent side right there. And we find the acceleration because this is a smaller number than this. We said the acceleration is going to be to the right, which doesn't feel like it makes sense, and I'm hesitant to leave this example without further checking that that's going to be a possible thing, that this one can be to the right but this one can be upwards right here at the same time, if that's a compatible thing. But I suppose it's in some respects a product or a consequence of the thing rotating, having an angular velocity. It's not impending motion, it's actual motion. So one is accelerating to the right, while the other one is decelerating upwards right there. Okay, so, but once we have this was our main goal, we can proceed to the rest of the example. And I probably made this overly long, but I figured I would continue with it because I had put in, this is actually from my book. I tried to make harder examples in my book, and maybe I should have picked a simpler example as my first one. The other examples are a little easier. Okay. And so I'm redrawing these. I don't see much of a benefit in trying to cram things into the diagrams. What I'm writing here, I'm going to look for the acceleration of C this time. That was our main goal. And so we get the acceleration of B, because that's what we know, plus the acceleration of C with respect to B in the tangential direction, plus the acceleration of C with respect to B in the normal direction. And let's put the labels on here. So the acceleration of B, so I guess I'll write it over here. Acceleration of B, that's terrible. A little bit higher. Acceleration of B right here. And we're going to pivot it about B, because that's the known, and the acceleration in the normal direction at c, it's going to be right there. So that's going to be the acceleration of c with respect to b in the normal direction, which of course we know to be omega squared, and this time that's going to be LBC right there. And if we were looking at angles, we know that that right there is going to be our 25 degrees. In terms of our angular, let's see, I'll use purple there. We just found out that our angular acceleration is in that direction. So we draw a c with respect to b in the tangential direction. We know that's going to be alpha LBC. We know it's going to be upwards. And let's be careful with these angles. We know that we have 25 degrees right up in here. Okay, so we're able to break the thing down into the x and the y. And on the left-hand side of this, I will put in the acceleration of c in the x direction, acceleration of c in the y direction. And so in the x direction, we get acceleration of a c in the x direction is going to be equal to, well, I didn't draw it on here, but that's the purpose of this. The could be 0 here in the x direction, right here at that spot, and then it's going to be positive alpha, which has a value of 0.05808, and then the LBC, which I believe was 6 feet, yes, 6, and it's only going to be the sine of 25 degrees. All right, and then we have for the normal direction, minus, because it's passing, you know, the x component is to the left, omega squared, which was 0.4138 squared times our 6, and that's going to be the cosine of 25 degrees. That looks like it's 75 right there, the cosine. So we end up finding that the component is in the negative direction, 0.7839 feet per second squared. And in the y direction, we have ACY is equal to, okay, I think we were given, it was upwards of 0.5. Hate those things. And then let's take a look at the tangential direction. That is upwards. You can see over here, that's an upwards of 0.05808 times 6 times the cosine of 25, and we add in, it's going to be adding, we have a positive because it's in that direction. We know it's right there, for the 0.4138 squared times 6 times the sine of 25, and the results of this are 1.250 feet per second squared. So the answer is a negative 0.7839 I plus, well, that's of course, that's using vector notation here, feet per second squared. We would usually also want to know the magnitudes here and the angle. That magnitude ends at 1.476 feet per second squared, and the angle I usually struggle with deciding what to use as a symbol for that. Let's just take, we'll call it theta C to give it some kind of name. And that's going to be rise over run. So that's going to be the 1.250 over 0.7839. And we get an angle of 57.91 degrees. Got to be careful where we're pushing that. We know that we have a positive y and a negative x, so it's going to be a quadrant that's to the upwards and to the left. So the answer is going to be 1.48 feet per second squared, this quadrant of 57.9 degrees. And that is the answer. It's a very long problem. Should probably have not have asked for point C, but it was. I wrote this problem as a demonstration of the process and thought that the main thing that I find as useful in this example is that we start by asking for that acceleration at C, and we don't solve directly for it. We actually have to do the side analysis where we first take and look at what happens at A, because we know something about A, that it's constrained to be in the horizontal direction. So with that knowledge, we're able to find the angular acceleration, and then we're able to proceed and go and find what the acceleration of C is going to be. So I guess I'm trying to make excuses for picking a really long example, but fortunately it's a video. That's Unchained off of the Fair Warning album. It's probably my favorite Van Halen song. I don't know why. I just like it. But anyway, let's end the example. Discard all that stuff. And it was a 22-minute example. Wow!